Lesson 4.3, Proving and Applying SAS and SSS. Looking at two triangles, we can prove triangle congruence with a couple of options. The SAS, or side angle side theorem, says if two sides and the included angle of one triangle can be congruent to two sides and the included angle of another one, then the triangles would have to be congruent to each other. The key thing here is the angle has to be in between the two given sides. It goes something like this. If AB is congruent to DE, that's where those double dashes are, and BC is congruent to EF, over on that right-hand side and over here on the right-hand side, and angle B is congruent to angle E. So notice angle B is in between those two equal sides, and so is angle E down here on the bottom. Then the two triangles are congruent, and we write by SAS. That would be our proof reason. Another theorem option for us today is called SSS, and that's side, side, side. If you can match up the three sides in any given triangle to consecutive sides in a second triangle, then the two triangles are congruent. So it says if JK is congruent to MN, we've got that double dash on the left of each triangle. JL is congruent to MP, and there's where that triple dash is, and MP is up here at the top. And then KL is congruent to NP on the right-hand side. Then the two triangles are congruent by SSS. Now, sometimes they won't be marked for you, and we'll have to figure out, well, what makes the sides and the angle in between congruent? We'll use some other proof reasons that we know. But then the next theorem talks about, well, what about the parts that weren't currently marked? This is called the corresponding parts. Whoops, I didn't mean to erase it, or cross it off, sorry. The corresponding parts of congruent triangles are congruent theorem, or short CPCTC. That's just fun to say anyway, kind of like ItBat. So CPCTC. What this means is if you know two triangles are congruent, anything that isn't currently marked, that as long as it matches up, would automatically be congruent to each other. So again, corresponding parts of congruent triangles are congruent. CPCTC. It says if triangle ABC is congruent to triangle XYZ, notice nothing is marked. It says then AB is congruent to XY. That would allow us to put a dash on those two segments. BC is congruent to YZ, that would get a double dash. AC is congruent to XZ, and that one would get a triple dash. So we know those corresponding sides would be equal, and so would the corresponding angles. A would be congruent to X, and so on. So anything that isn't currently marked, once you've proven triangles congruent, would be true because of CPCTC. When trying to verify the triangle order, make sure that you know all the corresponding parts in one triangle match up with the other ones. And then it really won't matter the order you start with the first letters. It says given two triangles with two pairs of sides congruent and the included angles congruent, that's important, verify that the triangles are congruent. So notice we have two sides on triangle RST and angle S is in between them. We have two sides on triangle XYZ and angle Y is in between them. Based on this grouping, we could write triangle RST is congruent to, it looks like angle R is going to match with X, S is going to match with Y, they both have that congruent symbol or that mark on them, and then T would have to match with Z. Now the reason that we either have SAS or SSS, and it looks like this would definitely be the SAS theorem, side, angle, side. And that's all you have to state. The second one, what rigid motion or composition of motions shows that triangle UVW maps to triangle XYZ? So we can see the grouping of the marks. We see that VW and YZ are congruent. Angle W is congruent to angle Z in the middle. And then UV and XZ are congruent to each other. So a rigid motion is either going to be a reflection, a rotation, a translation, or a glide reflection. It looks to me like we could just draw a line right through the middle and say that triangle UVW just reflects over to triangle XYZ. So I would think this is simply a reflection. And the two triangles would be congruent based on our markings, SAS. And again, remember, sometimes we won't have a lot of given information already marked on our picture. It says Allie cuts two triangles from a rectangular piece of metal along the dashed line to make earrings. How can Allie show that the earrings are the same size and shape? Well, here's where we have to look at the given information in the problem itself. It says Allie cuts two triangles from a rectangular piece of metal. Go ahead and circle or bubble or underline rectangular piece of metal. Because of the definition of a rectangle, we would know some things about the picture. We know that the left side, AB, would be congruent to the right side. So we could say AB is congruent to CD. And that's just definition of a rectangle. Opposite sides are equal. We also know that AD on the bottom would be congruent to CB on the top. And that's also definition of a rectangle. Opposite sides are equal to each other. So we can say AD is congruent to BC. And that's the same definition. Now let's see what else we know. If we look at that segment in between them, BD, notice BD would be on the triangle at the bottom and the triangle at the top. And BD is automatically the same in both triangles. So BD is congruent to itself. And that's because of the reflexive property. Remember our properties we talked about in topic 1B? That's one of the ones that we're going to use probably quite a bit in this chapter. So because those two sides are the same and they're on each triangle, it's automatically congruent to itself. When we look at our markings now, triangle ABD would then be congruent to triangle CDB because of that side-side-side congruence theorem. So that's us using some information about the definition of a rectangle and then the reflexive property to prove the triangles are congruent. Let's try another one. It says, given that AB is parallel to CD and AB is also congruent to CD, how can we show that angle B on the far right is congruent to angle D on the bottom left? In order for us to prove something about a particular part, we first have to verify that the triangles are congruent. So show the triangles congruent first. So we already know AB on the top and we know DC on the bottom. We know that to be true. Just give that the same dash there. Hang on. I just mixed up that dash. I don't want to do that and mess that up for us. We are? All right, so we know that's true. But then again, we know some other things about this part right here. When we have parallel lines, we know about different kinds of angles. The angle on the top and then this angle down here at the bottom would be congruent to each other because they are alternate interior angles. We haven't seen that in a while. This would let us write angle BAC is congruent to angle DCA. And that's because of the alternate interior angle theorem. AIA, alternate interior angles. So notice we have DC and BA. We've got angle A kind of up in the top left and angle C on the bottom right. And then again, the two triangles share a common side. They share AC in the middle. So that's another thing that we could say pretty easily. AC is congruent to itself simply by that reflexive property. Now we have SAS. So we have two sides and the included angle. I'm going to first start with the triangle on the top right. That's a weird triangle symbol. Let's try that again. All right, let's try that again. Triangle, if I go ABC at the top, is congruent to, let's see, angle A would map with angle C, and then D has to go in the middle, and then up to A. And that would be true because of SAS theorem, the side angle side. Now, here's the fun part. Once you know the two triangles are congruent, we can then say whatever's left in the picture, angle B is congruent to angle D because of the corresponding parts of congruent triangles are congruent definition, CPCTC. Anything that isn't already marked can now be marked as long as it matches accordingly. And that's what you have to do to show they're congruent. Here's another version. Find the value of x. Well, if we look at the two triangles, I noticed that the triangle on the top has 3 sides marked, and they correspond with the 3 sides on the bottom. So we would say here the triangles are congruent by the SSS theorem. And if that's the case, then x would equal 92 simply because of CPCTC again. That's a corresponding angle up on the top, all the way down to the bottom. So x automatically equals 92. Which of the following pairs are congruent by SAS or SSS? In this first picture, the two triangles are congruent because of SSS. In that second picture on the right, the two triangles, if you look at their location, notice you'd have to flip this kind of triangle down here to the bottom, but these two would be congruent because of SAS. Not every picture is as seems though. Let's take a look at the next one. For this bottom picture down here, notice we have 2 sides on each triangle, but the angle isn't in between them. So it's supposed to be over here in between, but it isn't. When this happens, the grouping isn't one of our 2 choices. So at this point, there's not enough information to prove them congruent. So we would just say not congruent. All right, one last one. If we go over to the triangles on the right, it looks like we could rotate this guy up and over, and then the 2 sides would match up, and that angle would be in between. Therefore, the 2 triangles would be congruent by side, angle, side. What additional information is needed to show triangle ABC is congruent to triangle DEF by side, angle, side? Well, if we look at the picture, BA is congruent to ED. That's a side. Angle A is congruent to angle D. That's an angle. So if we want to use SAS, we need another side. And it matters which one we pick. We have to pick the one where angles A and D would be between. It looks like on that first triangle, I would have to have segment AC. And on the second triangle, it looks like I would have to have segment DF. In order for us to prove the 2 triangles congruent by SAS, we would need AC is congruent to DF. If we could figure that out for some reason, then we could say the 2 triangles were congruent to each other. But then it says, well, what about trying SSS? So if we want SSS, that means all 3 sides have to match up. And again, so far we only know BA and DE. So we also would need AC and DF, just like the last one. But then we'd need BC at the top and EF at the top. So we would need to know that piece of information as well. If we were given those 2 pieces of information along with what's already marked, the 2 triangles would be congruent because of SSS. Let's try the last example. Is triangle STU congruent to triangle XYZ? Explain. If we take a look at the picture, let's see, ST, so TU matches with YZ. So TU matches with YZ. Those orders work. SU matches with XZ, so SU and XZ, that also works. Angle U matches with angle Z, and it's in between. So yes, they are congruent. And the explanation would be because of the side, angle, side theorem. The 2 sides and the corresponding angles for each triangle match up. All right, last question. Is any additional information needed to show triangle DEF is congruent to GHJ by the side, angle, side theorem? Explain. Well, it looks like we have 2 sides and an angle marked, but based on the location for the angles, E and H are not included. So while they're congruent to each other, they're not in between the two parallel sides. So what else would we actually need to make this happen? The angle that's in between on triangle DEF is actually angle F. And the angle for triangle GHJ is angle J. So we would need angle F is congruent to angle J. Why do we know that? Because the angle must be, whoopsie, forgot must. Hang on, sorry. There we go. The angle must be between the two marked sides. And that's included. So the two marked sides, that would be the included angle. If we knew that, then we would have enough to verify the triangle is congruent by side angle side. And that's your lesson for 4.3.